Hello, everyone. Welcome to this recorded talk for RECOMB on fast alignment-free sequence similarity estimation by tensor sketching. Let us discuss the motivation for alignment-free approach to sequence analysis. First, a fundamental problem in bioinformatics is to identify similar sequences in a large pool of biological sequences. And this arises in metagenomics or phylogeny or assembly, and all of them, the challenge they have in common is that presence of biological variation or sequencing error. And the alignment-based approach deals with this variation by solving a combinatorial problem, which typically grows quadratically or worse than quadratic with the length of the sequence or the number of sequences, which is not scalable to the magnitude of data, the terabytes or petabytes of data that we currently have due to high throughput sequencing. So the next thing, naturally, we need to innovate more on the algorithmic side, but I'd like to argue that we need better sketching algorithms. And the reason is because in sketching, we preserve relevant information with one pass over the data. And so at all times, we avoid loading data into memory, which is very scalable. And we can also make approximate distant queries in constant time, which is down from quadratic. So this is obviously very desirable for bioinformatics. And these are the benefits we gain if we focus entirely on a good sketching approximation. And now let's turn our attention to our evolutionary distance model. So this a very basic model is actually, we can view this as a noisy copy machine. So here A is deleted, G is substituted, and finally T is inserted. If we simply count the number of different positions, and in this case, we would end up with with 4, which is overestimating their distance. And the reason is because the two indels have introduced some frame shift, which is impossible to recover for this metric. The alternative is edit distance, which actually accounts for insertion, deletion, and substitution by a penalty of 1, and is clearly a better match for our setting. So the main takeaway from the example is that by estimating distance from contiguous pieces of the sequence, we will overestimate. And in a case of having here, we can actually fall into chance load. So meaning that two random sequences have a Hamming distance with length 5, would have a Hamming distance of roughly 4. And so basically from the point of view of Hamming, they're actually randomly related or unrelated, while they have 3 out of 5 characters in common, which is not actually random. So this is, this observation is behind our design, our method design, and we try to keep our method resilient to a large number of indels, such that it's resilient to these frame shifts. So now let us discuss our method, which is going to be in 3 steps. So tensor embedding, tensor sketching, and tensor slide sketch. So the tensor embedding, in case we give it for a special case of 2-dimension, which is 4 by 4 dimensional matrix. So each row and column corresponding to 1 character in our alphabet. And each element in the matrix is the count of that pair appearing in the sequence, or with arbitrary number of gaps. So for example, G appears before A, so we increment G, row G and column A, and G also appears before C, so we increment row G and now column C, and so on. So we go we iterate through all these pairs that one appears before another. So the first one determines the row, and the second determines the column. And to contrast this with the Kramer approach, so the substring, for instance, a tumor would have to be contiguous, but here we're now allowing this to be to have many gaps, basically arbitrary number of gaps. And therefore, there is no restriction or dependency between this base pairs. So now having this, we can also easily generalize it to more than 2 dimension. In that case, becomes for t dimension, it becomes a 4 to the t dimensional tensor, and then corresponds to a tuple of size t. But the next question is actually, how do we define that metric or distance for this 2 tensors? If we look simply at the difference between them, we can see some pattern emerging, which is roughly corresponding to these deletion and insertion and substitution. So for instance, the deletion of A has zeroed out the first 4 elements, these 2 elements in the row, which made these elements more positive in the difference. And the insertion of T had the opposite effect of making these elements more negative, which it tells us basically that the Euclidean distance between the tensors could be a good proxy for edit distance. And this is an insight, but we next try to formalize this notion of approximation. One way to do that is basically we can be viewing this from prism of statistical significance. So it's similar in a sense that we quantify how well does the metric detect a mutated pair from a random pair. So more precisely, we take a sequence X, we mutate it by a rate R, and then we compare that pair to another sequence which is entirely random, sequence Z. And obviously, if this metric is working well, there should be very few cases that it confuses them with a random one. And if it's not working well, they could be seen completely as random, which means there is a 50% chance of being more or less than random. And this plot exactly showing that. So for the left plot is that the x-axis is a mutation rate, the y-axis is the probability of basically detecting it as random or not. And for lower mutation rate, both edit distance, so the black solid line is the edit distance, the ideal, the orange line is our tensor embedding distance. And we can see that both they perform basically perfectly at lower mutation, but in higher mutation rate, in the extreme rate of 100%, basically they both fall into chance, that's 50%, and that's expected. And in the middle, you can see that the edit distance is performing better. So that's the ideal one, obviously, which is also expected. But the right plot is just taking a logarithm, which is also depicting bits of information about the sequence. So now we can see the drop basically in the drop between, or the gap between edit distance and tensor embedding distance is basically how many bits we lose by sketching or by embedding, in this case, the sequence into a tensor. Now, next thing to turn our attention to is the complexity. So obviously a tensor is, as we define, is 4 to t dimension, and is it's very expensive to compute and also expensive to store. Now, tensor sketching is exactly dealing with this problem by reducing the dimension from 4 to the t to d dimension, where d is a small constant. So in all these plots here is 30, and it does so in an efficient way. So it only is a constant factor more expensive than linear factor. So linear in the length of the sequence. And that says that the drop in the drop in performance, for example, here the blue line is the tensor sketching compared to the orange line, which is the tensor embedding, is very insignificant compared to the speed up, and is the very good trade-off between accuracy and speed. So here we see that the tensor sketch is basically preserving whatever was preserved by tensor embedding, while it's actually performing or computed linearly in parameters. And the only maybe issue we can see with this method is that by allowing this base pairs to be far apart, basically to have an arbitrary number of gaps, there's also maybe some insensitivity in lower mutation rates. So preserving global information, but not much of local information. And that's what we try to recover in Tensor slide sketch. So in Tensor slide sketch, we basically take sketches over a sliding window, and then we concatenate them into one sketch. So by introducing this window, now we restrict the gaps only to this window, which is shorter than the sequence length. And now we have introduced this locality, which improves our performance in lower mutation rates. So that's what we see here in the red plot. The red curve is essentially closer now to the edit distance curve. So now we're bringing it across the board closer to the edit distance. And you see it in both the left plot and also the information plot. There's another actually thing shown, which is the mean hash over k-mers. And that's just to contrast it with a substring-based approach, that Tensor sketch and slide sketch are actually preserving something which cannot be preserved with relying on k-mers. And that is actually not expected, because in high mutation rate, so let's say in 10% mutation rate, every 10th base pair is, let's say, an expected, it's expected to have one base pair mutated. And in 20%, every 5th base pair, and so on. So it's natural that relying on k-mers, it wouldn't lead to a good performance for higher mutation rate. While for Tensor Embed and Tensor Sketch and Tensor Slide Sketch is the opposite. So we don't have this adjacency or dependency between adjacent base pairs. Now, let us see the basically how does it perform in practice. And in terms of the speed, it's actually extremely fast. So for instance, on a single core CPU, Tensor Sketch and Slide Sketch are 5 and 25 megabase per second. And actually on a GPU, they're much faster. So Tensor Sketch is 200 megabase per second. Megabase pair, just to put into context, we can sketch in human genome with this rate in about 15 seconds. So it's a blazingly fast algorithm. And the performance also, you can see that it's much better in higher mutation rate, and it's also comparable in lower mutation. And I'd like to also share with you a small demonstration of the method in the Google Colab, which is in this link. So bit.ly/Tensor Sketch. You can simply go there, and you can visit this live experiment. So I'm going to show you. And here you have all the implementation. You can have a more in-depth look in the method or in how the sequence generation works. And plus, you have the parameters. You can basically run the experiments that I showed, the plots in the slides, and get probably also what parameters that you're interested in by simply running this live demo. And I also I'd like to point out that you feel free to share to edit this file for yourself and explore different options and share it and distribute it. So now let me just show you the one result. So what I just ran right now, it gave me this performances, which is for CUDA implementations is 20 and 26 megabytes per second. And on our setup was even faster because you can get better hardware than commodity there. So finally, let me get back to the presentation and conclude. So we saw that Tensor Sketch and our contribution was Tensor Sketch and Slide Sketch, and we saw that they will perform far better in distant sequences when the mutation rate was high. They admit dynamic sketching, and so we can stream over the sequence. They can be highly optimized both on CPU and GPU, and it's very much for future work interesting to see their applications. And finally, also to see how well we can actually compose them with other methods. With that, I'd like to thank my co-authors, Andrew Coles and Gunnar, who's my PhD supervisor. And I'm very also thankful to my BMI fellow members Ragnar and Daniel, who helped with the repository, and especially Ragnar, who wrote the CUDA, highly optimized CUDA code. And I again remind you that feel free to go to this demo and see this method for yourself. I hope that you enjoyed the talk, and thank you for your attention.